from online now through the Teams meeting. Hi guys in the meeting, can you guys hear me? Oh, okay, that's great. Okay, we finally figured out. So I just mute myself on this laptop and I unmute myself on this desktop. And then I use one of the microphones here so that people from online can hear me and we don't have an echo in this classroom. So that's the final solution for this. Oh dear. So, all right. Oh, finally, let's get started. So in our last lecture, we have learned about an introduction to software testing, and this is, can I just pop out? Okay, it's better now. Okay, so in our last lecture, we have learned about the basics of software testing and why do we need to do testing. And we touched a little bit about verification and validation. So in short, verification is about, are we building the product in the right way? And validation is about, are we building the right product? And that's the difference between verification and validation. And testing is considered as a technique, a validation technique. I think this microphone is not very, it is not very stable. I'll try another one. Let me try, oh, this one is better. So there are so many problems with the classroom. So let's continue. So software testing is considered as a validation technique. And most of the validation techniques are considered as dynamic software analysis techniques. And I hope you can still remember what is the difference between static and dynamic in the context here. So let's move on to today's content. Today we will cover 3 more aspects or 3 more groups of concepts, and then we will warm you up with some code of Python. So you will be using Python for coding your assignments. So we will warm you up. And there are many different types of verification and validation techniques. And we are going to focus on the testing techniques here. So we are going to focus on the dynamic ones, and we are not interested in those static ones. So in the next week, we will learn about some black box testing techniques. And in the next week, we will learn some white box testing techniques. And these 2 will be used for your assignment 1. And then we will learn gray box testing, which is one of the most practical testing techniques for finding vulnerabilities in real-world applications. And we are not going to learn any of these static analysis techniques in this course. However, in order to understand the advantage or the disadvantage of dynamic testing techniques, we need to touch a little bit of the static methods and compare it with the dynamic method. And like we discussed in the previous lecture, the static analysis is like we are going to scan through a piece of software with some patterns and rules and look for potentially buggy or vulnerable patterns. So given a piece of code, we are just going to look for some specific patterns. For example, the access of an array index without checking the index value. And there are many methods for doing static analysis. One of them is to do formal verification, which was taught in COMP 3141, and this is often done manually with the help of some formal analysis tools. And another type of static analysis is called software component analysis. So modern software is normally made up of many different components, like some third-party libraries. And some of these libraries could have bugs or vulnerabilities. So if we can identify the versions or the components of the software accurately, then we may know that, okay, this software is using some buggy library, then this software itself could be buggy, right? So that's software component analysis. And then we also have static tint analysis. So tint analysis is like we are trying to tint some values or some variables inside the program and track how does the value propagate through the program execution. So this could also help us to understand how does a program work. And for dynamic analysis, the difference between static and dynamic is whether we need to run the program to do our analysis. So for dynamic analysis, we need to execute the target program and observe the system for some abnormal behaviors. So static analysis, although they are very powerful, they are not good at discovering problems during the runtime. So there are certain program behaviors that could only be analyzed from runtime. For example, if we want to calculate how is the execution efficiency of a program, then we have to run it. We have no other choice. So dynamic analysis could be used to help with these runtime verification or runtime analysis. And more often, dynamic methods could be cheaper than static ones because they are easier to automate. Most of the static analysis techniques, they require certain levels of manual effort. For example, if you want to do a scan through the program code, you have to write the rules manually, right? Or if you want to do formal verification, then you have to sit there, use the formal verification tool. So normally dynamic methods are easier to automate. So given these characteristics of static and dynamic methods, let's do a live poll. So which systems do you think could be formally verified? Like formal verification is like using a verification tool to verify certain properties inside the program, like whether a loop will terminate after 10 times, like whether a function will be invoked eventually in this program execution. So which of the systems do you think could be formally verified? You can have more than one choice here. Actually, all of them could be formally verified. All of them are. Can you try to scan this QR code? You can also try to visit this page on WebCMS, so you can see it. Oh, there's no upcoming date for this, okay. But you can also find it from the Activities tab here. So actually, all of them could be formally verified and are suitable for formal verification. And because all of them are, there are some of the compilers, not all compilers are small programs, but some compilers are very small and they are very, very important. So people are formally verifying them manually. And some OS kernels are also formally verified because operating system kernel is like one of the most important software in a computer system. So people need to ensure the security of these problems and they need to verify these. And another important type of software that could be formally verified are the smart contracts, because smart contracts are directly linked with real money, right? So, and they are often very small, they are like a few hundred lines of code. So these smart contracts are also normally formally verified. And there are some big companies doing these formal verifications for smart contracts, which can earn a lot of money. So there are so many verification and validation techniques. So how do we determine which one to use when we are doing quality assurance? So normally, this is a game of trade-offs. We need to consider the resources we have in our hand. So we need to figure out what we want, what we need, and most importantly, what we have. So we can't have, like mentioned by a NASA engineer, so better, faster, or cheaper. We cannot achieve all three of them with one single technique. So we have to do a trade-off here. So for most importantly, because we are doing quality assurance, we want things to be better. And however, sometimes we have to always satisfy the quality here. We must be able to tolerate some kind of inaccuracy when we do analysis. So there are three types of inaccuracy here in this system. So the first one is pessimistic inaccuracy. So we might be very pessimistic about the program, and we may not guarantee, so a technique may not guarantee to accept a program even if the program possesses certain properties. So this will give us false positives. So even if a program, so sometimes even if a program does not have certain errors, a tool may still report an error here. For example, if we write certain rules or certain patterns to do static analysis, it is very likely that we are going to match some benign code. So we will have this kind of pessimistic inaccuracy when we do this kind of rule matching or pattern matching for static analysis. And on the other hand, we may also have optimistic inaccuracy. So we may accept a program that doesn't have a desired property. So this will give us false negatives. This means that there is a bug, there is a vulnerability in this program, and our rules or our technique couldn't find it. So that is optimistic inaccuracy. So, and the third one is the nature of the complex nature of the program we are going to test. So, because we are checking different properties of the program, and if one property is too difficult to check, we may substitute that property with an easier to check one to make sure that our method works. But in this case, we are introducing inaccuracy. For example, if we want to check the implementation of an HTTP protocol or HTTP server, we can model the entire program as a state machine and do some kind of checking of the state machine. But in that case, if we couldn't model if the state machine we propose couldn't capture the actual implementation of the code, then we are introducing inaccuracy here. So that's due to the property complexity. So these are the three sources of, or three types of inaccuracy. And for testing techniques, we are more likely to have the optimistic inaccuracy. So that means for testing techniques, we are very unlikely to have false positives. Because if you run a program, it crashes, then it must mean that there is some kind of bug, right? So, but if you run a program and it doesn't crash, it doesn't mean that this program is free from bugs. So that's why testing technique often have no or very few false positives, but it may suffer from false negatives, which means that we may not be able to detect certain bugs. But once we report that there is a bug, then it is a real bug. So this is the characteristic of testing techniques. And talking about false positives and false negatives, we need to mention two key terms that you may encounter when you read the literals about testing and program analysis. And these two terms are soundness and completeness. So a technique is sound if and only if it only identifies true positives. So this technique is sound. It means that this technique will not report false positives. So it's sound. And a technique is complete if it can identify all the true positives. It means that, so a technique could be sound but not complete. Then it means that every bug reported by this technique is a real one. But this technique may not be able to identify all the bugs inside the program. And testing technique, most of the time, is sound but not complete. And that's all about the theoretical aspects of verification and validation. And now let's move on to how do we use them when we are doing software development. So when we are doing software development, we need to plan how could we use different verification and validation techniques. And this is called software V&V planning. So the planning is like very important for most of the development work, and there are multiple levels of testing plans that could be developed according to the various levels of V&V activities. And there are 7 steps in total. So the first step is to identify the goals of verification and validation. So the verification and validation goals must be identified from the requirements or specifications. So like in software development or software engineering, what we do first is to try to fix the requirement or specifications from the users, right? So this is to make sure that our final product is consistent with what is required or specified by the users. So the first one is to make sure to have these goals, and these goals are coming from the specifications and requirements from the users during the software development. And the second one is to select usable or suitable V&V techniques for this project once we have figured out the goals. And there are many different criteria for this selection process. And during each one of the phase, there are different techniques suitable for them. And you don't get overwhelmed by all these concepts. They are just trying, and these are not really accessible for in your assignments. But this is just to make sure that, okay, you have this kind of concept in your mind, and you don't have to recite all of them. You just need to know that, okay, roughly I need to follow these steps. And when you actually do things in practice, you just remember, okay, you have to do this, and you can refer back to these slides. And after we have selected a suitable technique according to their characteristics, we now move on to the third step. We need to figure out what are the responsibilities from different parties or different teams in the software development team. So so there are many different actors or different roles in this software engineering ecosystem or the development process. So for the developmental organization, which is often the software developers, their responsibility is to construct any applicable proof of the correctness at module level. So this means that as a developer, most often we are in charge of doing some kind of unit testing to do module level assurance of the correctness. And in many big companies, there might be independent testing team. So for this team, most often they are going to ensure their responsibilities are to ensure the quality of the entire product or the entire system. So most often these independent testing teams, they are doing some kind of system level of testing instead of unit testing. And apart from the independent testing team, there could also be some quality assurance team in these companies. So these quality assurance teams is to make sure that the software meets the quality to be released, and they will do some property-based testing. For example, they will test the actual performance of the software instead of looking for logical bugs. And another level, the last layer of this organization is the independent contractors. So sometimes some companies may outsource the testing tasks to some third-party people. Like, for example, some big companies, they may have bug bounty programs to allow others to help them to test their programs. And the step 4 of this planning process is to integrate the selected V&V technique. So this is often dependent on the development methodology. So it depends on whether we are doing waterfall development or agile development. So, for example, if we are doing agile development, we can try to integrate the testing as part of the CI or CD process. So this is the step 4. And step 5 is about program tracking. So before step 5, we are talking about, okay, how do we determine the responsibility of different parties? How do we select different tools? How do we integrate the quality assurance techniques into our system? And after that, we may find some problems or some bugs. Then we need to do proper problem tracking. So this often involves. So this is to document our effort during the V&V process. So we need to keep important information of the problems or the bugs. So there are several typical information to be kept. So one of them is, when did the problem occur? So this is often related to, so some bugs are time sensitive. So we need to make sure that we need to keep track of when did the problem occur. And we also, of course, we need to know where the problem occurs. So we need to know which part of the system went wrong, or even which line of code is causing the bug. And then it's better to keep track of the state of the system before the occurrence of the bug. This is to help us to replay and debug. And of course, we need to have evidence of the problem. So evidence of the problem could be that the program crashes, and it could also be some input that is causing the crash. And lastly, we need to assign a priority to the problem. And assigning priorities could be according to the severity of the bug, like whether the bug is a vulnerability or not. So this is also related to the safety property of the software dependability. So an advantage of using testing technique as the V&V technique here is that we can use the test cases that triggers the bug as the evidence here of the problem. And if we just do static analysis, like doing the scanning, we may not have such evidence that is really a bug. So this is the advantage of using testing here. And for step 6, after we have kept track of the problems, we also need to track our testing activities. So because most of the time we couldn't find any bugs in our system if we do testing or if we do validation. So we need to have some kind of record about, okay, we have done this, we have done some proper testing technique. This is not only to keep track of, to maintain an internal record, but also to make sure that some third-party compliance trackers could verify that, okay, this organization has done some testing properly, so the product could be trusted to a certain level. So normally we need to keep track of these data. So we need to keep track of the number of test cases executed, and we also need to track of the number of tests that are not executed yet. We may also need to track the time used, resources used, and number of problems found. And the last step is to do assessment. So it is important for the plan to provide the ability to collect data. And make sure that it is used, make sure that this we could assess not only the final quality of the product, but also the verification we have done for this product. So this helps us to provide a proof or guarantee that this product is trustworthy. So that's about assessment. So it's not only assessing the product or the testing, is like we assess both of them together. So these are the 7 steps of doing V&V planning. So you don't have to worry about memorizing all these concepts. This is just to show you, okay, there is such a thing. You need to consider about it when you are really doing testing or quality assurance. And there's one more big chunk of concept before we jump into some code. So let's learn about principles of analysis and testing. So there are 6 principles for doing analysis and testing. So these principles, you may also find these principles to be usable in the actual testing techniques we will learn later. So they are reflected by the design of those testing techniques, and I will introduce them for now. So the first one is sensitivity. So we must make sure that our testing technique or our validation technique is sensitive to failures or errors. For example, if we run a program and look for crashes, we may miss out some bugs. For example, you can, if you are online or if you have the slides open on your laptop, you can click on this link. It will lead you to this one compiler page. So basically, this web page can help you to run some programs online. And in this small C program, we can see that we have a string or buffer with length of 8. And what will happen if we try to read from the 9th character? What will happen if we read this? Will the program crash or not? So normally this program doesn't crash, but there is an error, there is a buffer overflow here. So if we just look for crashes, we are going to miss this bug here. So if you click run, you can see the value was printed out, and there's no error happening here. So we need to be sensitive enough to detect this bug. And this is another example is, for example, if we write one more byte, if we click run, then you can see that the program crashes due to overflow, due to the buffer overflow here. So different failures requires different levels of sensitivities to capture. So the first principle is that it is better to fail every time rather than only on some executions. So it is better that if we can fail or crash on both cases, rather than we just crash on writing 10 more bytes but not reading 1 more byte here. So it's important for us to make faults easier to be detected. So by making them to crash more often, And one approach here is to use address sanitizer to compile the program so that it will crash every time an error occurs. So you will be using this later during this course, but not for now. So this is about sensitivity. And another principle is about redundancy. So it is sometimes encouraged to have multiple test cases or multiple testing mechanisms or different techniques to test the same functionality. So this increases the likelihood of catching errors. So we may use one technique to find this, to check this functionality here, to check this piece of software here, and it is often encouraged to double check this software with another technique from another angle. And even if we are using testing techniques, there could be different testing techniques here, so it's encouraged to use a combination of them. And one typical example is ensemble fuzzing. You will use this in your assignment too. So this idea is to basically combine different fuzzing or testing strategies to check for the same module. This is about redundancy. And the third principle is about restriction. So when there is no cheap way to check certain properties of the program, sometimes we can restrict the problem to reduce the complexity for checking the actual implementation of the program. So, or maybe we can try to focus on a smaller subset of the programs. An example is that an example is here. So for this program, we have an integer k here, and only if the condition of I is satisfied, then we assign an initial value to k. Otherwise, we just plus I to k. So in this case, we don't know whether this k could be initialized or not, right? So this is very hard to determine whether this k will be initialized the first time I is added to it, because we don't know what happened in this condition function call here. So a more simple way of doing this, of resolving this problem, is that we just don't allow all paths with potentially uninitialized variables. So we can somehow convert this problem into a cheaper one or a more restrictive one to solve it. So that's the basic idea of this principle. And the fourth one is about partition. So just to divide and conquer. So the best way of solving a big problem or a very complex problem is to divide it into some smaller ones. So one of the ways of doing this dividing is to divide testing into different levels. For example, we can do unit test, we can do system test. And remember, in the V&V planning, different parties could be in charge of different levels of testing. For example, normally the developers are in charge of unit testing, and the dedicated testing team is in charge of doing the system level of testing. And the sixth principle is about visibility and observability. So visibility is the ability to measure the progress of status against our goals. So remember, the first step in V&V planning is to have some goals according to the specifications or requirements. So we need to know, okay, we need to make our testing progress visible so that we know where we are. And we also need to make sure that the verification or validation technique is observable. So we can know that, okay, this testing technique is working here or it is not working here. So these visibility and observability are also important for these testing techniques. And the last one is to allow feedback. And this is to apply lessons from experience in progress and techniques. So in testing, this feedback or this experience-based principle is that we can prioritize our test efforts based on the likelihood of fault classes. For example, given a very big piece of software and a limited time budget, we need to decide which part of the software do we want to do testing, right? We may not have enough time to test the entirety of the software. We have to prioritize which part of the program do we want to test. And we can prioritize our testing efforts according to the complexity of different components. So a typical example is, or a typical assumption is that the more complex a piece of software is, the more likely it is to be buggy. So if we have limited time budget, we may need to prioritize or focus on the more complex parts of the program. And that's all about the concepts of verification and validation. And then we will move on to some coding. And this is to warm you up about and get you prepared for these assignments. And before we jump into the details, let's have a 5 minutes break. Hi Krishna, can you hear me now? Oh, I think he's offline. Have you guys learned Python before? Like before taking this course? Some of you have, right? Okay, that's great. And if you haven't taken Python before, this is a good chance to catch up. And if you have, this may provide you a different angle of Python from a tester's point of view, because I'm trying to cover some corner cases or some features that may cause bugs when you are writing code. Okay, let's get started. So, if you wonder where to find this material for learning basic Python syntax, you can find it from the lecture slides tab here. It's practical Python syntax. It has to be put under one of the weeks here, but we will do this in both week 1 and week 2. So let's get started. But remember, this is not a course to really teach you a programming language. So I assume that you know the basics of Python. So like, what are the integers, what are the strings, and how to do basic operations with these basic types of variables. And I assume that you know what is a class, what is an object. So you know some basic concepts of object-oriented programming. So have you taken the OOP course? Okay, great. So you know that in Python everything is an object, right? So like, let's have a quick warm-up about object-oriented programming. So like, all of us here are humans, and human is considered as a class, and we are considered as objects of that class. And like, these chairs are considered objects of the furniture class. So basically, object-oriented programming is just a programming paradigm to help us to describe the world using a programming language. So this course, as I said, is not the course to teach you Python, but let's try to cover some interesting language features of Python that you may make mistakes when you write the code, and try to warm you up and get ready for the assignments. So in order to use this document, it is recommended that you try out, there are a lot of code snippets in this document. It's recommended that you try out these snippets yourself with a Python interpreter, better with a version higher than 3.10. So this is how to use this document. You should first read the code and think about the output without actually running the program, and then actually execute the code and see if what you have thought is correct or not. So let's try to cover the is versus equals and mutability today. So do you guys know what is the difference between is and equals in Python? So what is the most common scenario of using is, the keyword is? Yeah, you roughly got the answer. So anyone else have a try? So what is the most common scenario of using is? Actually, the answer is here, is none. So if we check a value is a null value or none or not, we often use is instead of equals. And they are different. So let's try to consider each code block here. So you are encouraged to try it out yourself, and you can either use a Python interpreter on your local machine. For example, for me, I have installed Python on this laptop. You can see it's 3.12. Or if you don't have Python environment installed, you can try to use the one compiler cloud platform on your laptop. So in this platform, they have Python 3.12 installed. So you can just copy the code and paste it here and then run it. But the advantage of using a terminal-based interpreter is that I don't need to print out the results. It will automatically get printed out. It's very interactive, so it will print out the value of the variables or the return value of functions. So let's try out the first example here. All right. Wait. A equals to 1, 2, and B equals to 1, 2. Does anyone know the type of A and B here? Are they a list or not? Not a list? Yes, yes. They are tuples. They are not lists. So because we are using parentheses here instead of square brackets. So A and B are tuples. So what do you think will be the result of A is B? Without running the program, don't try to run it. So before running this program, what do you think is the result of A is B? True or false? True? False? Okay, let's run it. Remember, everything inside, every variable inside Python is an object. Is false. So because there are two different objects, and is used to check whether two objects are the same. What about A equals to B? What will be the result? True or false? True. Okay. The answer is true. So because equals checks the actual value of these variables, but not the identity of these objects. And let's try the second code block here. A equals to 1. Remember, A is still an object. A is still an object here. B equals to 1. So what will be the result of A is B? They are still objects, two objects of integers. What will be the result? Huh? False. And the answer is actually true. This is a little bit confusing. There are some small, subtle features of Python which could cause confusions, and I'll try to cover them using this course. I'm not trying to cover those basic syntax and all those things, but let's try to cover those corner cases. So A is B is true. What about A equals to and equals to B? Is it true or false? True, yeah, of course. So I will explain why this A is B is true here. But before, I'll try to answer it after we see another example. What do you think is the result here? 100K is 100K. True. Actually, it will also warn you you better not use is here. Actually, it helps us to fix this syntax here. And Let's continue. So what is A is B? Is it true or false? True? It's actually false. And what about A equals to B? True. This is quite obvious. So the reason is that so the first question, why, when we are trying to compare 10K versus 10K, the Python interpreter gives us a warning, and it says is shouldn't be used here, we should use this, and it automatically fixed the problem of this expression here. So, but why none could be used by using is, using the checker is? That's because of a language, a concept called singleton in object-oriented programming. A singleton is where a class has one and only one object, and the value of none is the only instance of the class none type. So it is the only instance. None is an object, and it is the only object of that class. So because it is an object, we can use is to compare with none. So that's why we can use is. And can we use equals to compare none? To compare with none? Do you think we can do that? So let's say A equals to none. What do you think will happen here? It is allowed, and it will return as false. So it is allowed because none is an object, so we can still use equals to check with it, to check the values against it, and we can also use is to check whether a value is none or not. But we still recommend to use is whenever we are trying to compare a value with none, because it is faster and makes the code clearer. And the rationale is whenever we are using is, it is actually comparing the unique ID of an object with the other one. So it essentially equals to this. So that's why is faster than equals to equals, because if we do is, we need to invoke this function here. We have extra function invoke. So this makes our code a little bit slower, but you won't feel it, but it's a little bit slower. And if we use equals, it actually calls this equal function here. And this is a built-in function for most of the objects in Python. And that's why if we use this operator here, we are comparing the actual value of objects. And if we use is here, we are actually comparing the identities of objects. And then you may wonder, okay, this explains why this A is B is false, right? So because there are two different objects, so this should be false. This also explains why A is B is false here, because there are two different integer objects, so this should be false. But why A is B is true here when they are both assigned with value 1? That is because a mechanism of the Python interpreters to speed up the execution. So Python interpreters, especially C Python, they are trying to store the small integers as some kind of internal values. And if, by default, if a value falls within this range, they are kept as small internal values. And if you assign variables to these values, they are referring to the same object. So that's why A is B is true if we assign value 1 to both of them. This will also hold if we assign some value like A equals to 200, B equals to 200, and then if we check A is B, it's also true, because they are kept as internal values by the interpreter. So when you write code, when you write Python code, you should be aware of these small things. And why do we learn this? This is also because it is also related to the mutability of different objects or different types of variables in Python. So sometimes when we write a Python code, we pass a variable as a parameter to a function, and then we do something with the parameter, with a variable inside that function. And sometimes the value of that variable gets changed, of the original variable gets changed. And sometimes the value of the original variable doesn't change. So let's try to explain in detail when will this kind of thing happen in Python and when the variables remain the same. So let's consider this example here. So we define a function AB, which accepts two parameters, A and B. And what we will do is we will add B to A, and then we will return the value of A with this function. So, and our task here is to observe whether the value of A gets changed during the execution of this function or not. So that's our task for this one. So let's try to run this. The return values of the code messed up in the PDF file, so I'll just use a markdown file here. So let's define the function first. And then let's try out the first example. So in this example, do you think the value of A gets changed or not? No? So what will be the value of A and what will be the value of B after executing this function? And also C. 1, 2, 3. Okay. Okay, seems most of you are saying 1, 2, 3. Okay, let's see. It's actually 1, 2, 3. And let's try a second one here. So now this time, instead of assigning integer values, we are creating two lists. So A is a list holding an element of integer 1, and B is a list holding a single element of 2. So, and C is this. So what do you think will are the values of A, B, and C after we execute the function? Will the value of A get changed? Yes? Will the value of B get changed? No. And what about C? So is C the same as A in terms of value? Yes. And what about A is C? Yes? Okay, let's try. No? Okay. So A, B, and C. So this time is different from the previous one. So in the previous run, A remains the same. A is still 1 after we execute this function. But this time, A gets changed. And this is actually a side effect of this function. We we just want to return this value of A, right? If we pass in the value of A to this function as a parameter, we don't want the value of A gets changed during this function execution. But it is actually changed. So this behavior, you need to be aware of this behavior. This could cause you some trouble when you write Python code. So A gets changed here. The value of A is changed here. And if we check A is C, what do you think will be the result? True or false? False, actually. Sorry, true. 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 Yeah. A is the same as C here. And we will explain why this is like this later. And what about A equals to C? Of course, true, yeah, because the value is the same, so it's true. And let's try another example. So in this time, instead of using a list, we are using tuples. So what do you think will be the values of A, B, and C here? Before running this code, what do you think? Is it the same as the first one or the second one? Just make a guess. You don't need to be so serious. This is not an exam, so just feel free to make your guess. So will the value of A get changed by this function or not? No? Actually, the answer is no. So A doesn't change here. So you can see that, okay, it seems that whether the value of A gets changed or not is not affected by whether A is a variable with a single value or A is a variable with as a list with or an array with multiple values, right? Because both list and tuples can hold multiple elements. So the only thing affecting this behavior of Python is about the mutability of the variable type. The reason that A gets changed is only because the value, the list, is a mutable type in Python, and integer and tuples are not mutable in Python. This could be reflected by this. For example, if we assign A as a list, then we can change the value of A. And if we print out A again, you can see the value of the first element of A gets changed. However, if we make A a tuple here, and what will happen if we do this? We will end up into some kind of errors. So it's immutable, because tuples are immutable. So if we pass in an immutable function as a parameter to an immutable variable as a parameter to a function, then whatever we do in that function will not affect the actual value of the original variable. However, if we pass in a mutable variable to the function, the value of the original variable gets changed. And you can imagine it as the function is holding a reference of the original variable inside it. So that's why if you do something here inside this function, the original variable gets affected. And since we are holding a reference of the original variable, so that's why the return value here, if A is mutable, the return value is actually the same as the original object. So that's why this returns as a true here. So you need to be very, very careful when you are writing Python code. When you are passing in variables and parameters, you may sometimes wonder, okay, why does this variable get changed in my code, right? So this explains why. And there are many mutable types types in Python, and some common mutable types are dictionaries, sets, and lists. So these are some common mutable types. So when you are passing them as variables, as function parameters, you need to be careful that their values might get changed by that function. And if you don't want the original value to be changed, this is a little bit too small maybe. If you don't want the original value to be modified, you should make a copy of that value whenever you are trying to modify a mutable variable inside your function to avoid this side effect. So what you can do is you can import the copy library, which is a built-in module of Python. And then you can try out these examples here, but the answers to these values are printed out here, so you don't need to make guesses. But let me explain a few of them of why they are not true or why they are true. So list is the constructor of the class of list. So this means that we are creating a new object of list with L. So in this case, we are creating a new copy of L. However, if we use this, it's also false. And let me hide this answers from here. So in this case, we are also creating a copy of L. And there's another way of creating a copy, and that is to use the copy function from the library copy. So in this case, we are still creating a new object. So all these three are three different types of creating copies of mutable variables. And it is the same for dictionaries and sets. So list, dictionary, and set are the three most common mutable variables. And sometimes in Python we can have default arguments for functions. For example, for this function f here, x is assigned with the default value of an empty list. So if we invoke f without passing any parameters to it, What do you think will happen here? What will be printed out? Yes, just a single, at least with a single value of 1. And what do you think will be printed out if we do this? Yes, 0, 1. And if we do it again, still 0, 1, right? But if we do this becomes 1, 1. That's because the default value, this default value is a list, it's a mutable value. And this, by default, Python, if we don't make a deep copy of this default value here, Python will try to reuse this object. So that's why the value gets changed. The default behavior gets changed. So, but if we assign a value to this, if we try to invoke this function again, it will become 0, 0. And what will happen if we invoke this function again here? What's the result? How many ones do we have? 2? 3. Actually 3. Because Python is trying to reuse, the interpreter is trying to reuse this object. And whenever we invoke the function without a parameter, we are reusing this default object, the default parameter object here. So that's why it keeps increasing. So this is also another behavior you should be aware of when you are using Python. So sometimes you may encounter some weird bugs when you write Python code, and this could be the mutability of the default value could be one of the reasons. So should be careful about this. And it is the same for the default values of class constructors. So I won't show it again. So the takeaway here from this example is that a mutable default argument is shared across different calls, as far as you don't overwrite the default value of that parameter with a custom value. So this is shared. So Python, this design is actually to save memory usage, but it could also cause you some troubles. And you should be careful that using this mutable default parameter could lead to some unexpected behaviors. Let's try one last example of mutability here. So what do you think will we get for L if we do this? What is L here? Like this is a really usable syntax for Python. We are trying to create lists. So this will give us a list of 10 empty lists. And let's try to print out L. You can see it's a list of 10 empty lists. So what will happen if we do this? Because L is a list of lists, so we can append elements to the element of L. So what if we append 1 to the first element of L? What will happen? What is the expected behavior? What we want is with 1 here, right? 1 and 9 empty lists. That's what we want to have with this code. Let's see if it works like what we expected. It doesn't. The value is copied for all the variables of all the lists in L. So do you know why it is working like this? Yeah, you got it. So if we use the multiply operator here, we are actually, and this is because this is an immutable, this is a mutable object. The element is mutable. So we are actually copying references to the same object 10 times. So that's why whenever we modify one of them, we are modifying all the values here. So this could be verified by doing this. Let's say, for example, if we do this, let's say append 2, and what do we expect to see from L? Like all of them will be 1 and 2. So because they are all referring to the same list object. So this behavior should also be aware of this behavior. So what can we do in order to create a list with 10 independent objects? What do we do? What do you think can we do? Can we do this? Can I do a deep copy here? Let's say copy, sorry. Copy the copy. Can I do this? Does this work as what we expected? Will this work? No? Why not? It's actually essentially the same as what we did before, because we are just passing one single object here. This is essentially the same. So, and we can verify this. So you can see that all values are modified. We are not creating a new copy. So the correct way of doing this, or the most elegant way of writing a piece of Python code to do this, is that we can do this. So this time if we print I, it still looks the same, right? But if we do value changes, you can see there are 10 independent. Okay, there are 10 independent lists. So this one line of code actually equals to this piece of code. So we initialize L as an empty list, and then for each integer from 0 to 9, so range is like from 0, if you don't specify the initial value, it's from 0 to this value minus 1. So from 0 to 9, every time we create a new object of a list, and then we append that object to L. So this single line of code is the same as these 4 lines. So in this case, we can create 10 independent list objects. And that concludes our today's lecture. So these Python syntax are not, you may use it in your assignment, you may not use it. They are not directly accessible, but I hope that this can warm you up and about Python, and you can try to, when we are writing code and when you are encountering some weird behaviors of the code, you will know why it happens. So this is the purpose of this material. So that's all for today's lecture. So in this week, actually, we are covering only some very high-level concepts, and in our next week, we will be learning some techniques of black box testing, which are related to how do we design test cases without having access to the actual code. So see you next week, and thank you for coming.
How many assessments do we have in this subject?
Two assignments, two quizzes.
And two quizzes. When do the quizzes happen?
After
And the assessments will happen. Assessments will happen in the beginning.
sorry?
The assessments will happen in the beginning.
Yeah, the first assignment will be, we plan to release it by the end of next week.
Okay.
The
This-
specification. And the due date of the first assignment is by the end of near the end of week 4, because it's before the continuous.
Oh, yeah. And is there any final exam for this?
No, there's no final.
Okay. Thank you.
Really? Are you losing your interest? Yes. And
I'm getting forward, you know? Yeah.
good.
So at the end of this,
Then the person who understands.
yeah, at the end of the term, he just won't even come.
Yeah.
No, I'll be standing there.
Every week, 1 week, like one seat behind.
Every lecture.
Sorry, is this your jacket?
Oh, yeah.
Thank you. break, I can have lunch as well, like you. Why not?
Go for it.
Yeah, next time I will do. Because